Hi, in this video, I would like to talk about the maximum likelihood. First, I will talk about the setup and the notation, and then I will move on and talk about the maths behind. It would be helpful for us to imagine a scenario before we introduce the concept of maximum likelihood. The scenario that I'm providing here is working or not. Let's say we have a dependent variable y. It can mean work or not. If it takes the value of 1, it means the laborer chooses to work. If it takes the value of 0, then the laborer takes the choice of not working. And here, this is a utility function. A utility function depending on a lot of characteristics such as the salary of the job providing, the working hours, the job characteristics, and so on. Beta t is just a vector notation for simplification, and e is the error term. It makes sense for us to think that if a utility is higher than a certain value, then the person, the laborer, would choose to work and would not choose to work if otherwise. So, converting that idea into mathematical notation, y, the dependent variable of work or not, it takes the value of 1 if a utility is greater than 0. In this case, let's just take for example. And the person will choose not to work otherwise. Or we can use this notation here. Y equals to 1, so the person chooses to work if, this is the condition, the utility is greater than 0. And what we're most interested in is the probability of a person working, because we would like to investigate on phenomenon, on what is the factors behind the laborer's mind that urges them to work. So the probability is very important to us and we want to know about it. The probability of y equals to 1 is actually equals to the utility greater than 0 in this case, in my example. And further manipulating, it's actually just equals to probability of the error term greater than negative beta tx given x. Now, in order to solve this probability, we need to specify a cumulative distribution for E. And in this case, in the probit model, this G is equals to a cumulative standard normal distribution. In the probit model, this is a standard normal distribution. In a logit model, it can be another distribution. So I use a G here is a more general notation, and this time it's equal to the standard normal distribution. The next time you might specify another distribution. Okay, so now using this cumulative standard normal distribution, we can simplify the probability to this form. And at the end, it will be simplified to just G beta Tx. So therefore, the probability of y equals to 1 given x is the cumulative probability of all the values below beta tx. Now, it will be helpful and for us to think of the difference between this nonlinear function and our usual OLS estimation of simple linear regression. The difference is that this is a linear relationship. It's just beta tx. But here we have a nonlinear function that represents the probability. We want to use this nonlinear function to capture some interesting phenomenon because we know that if the probability of working might depend on the position of x. So the nonlinear function captures something that the linear relationship couldn't. Okay, so enough of the setup and the notation. We'll move on to the maths behind. So the maths is actually based on a principle. The maximum likelihood is that we're trying to estimate the beta. And how do we do that? Is that out of all the possible values of the parameters beta, we choose the value that makes the likelihood of the observed data largest. What does that mean? That means that, let's say in an example of 3 observations, With 3 observations, 1 is working, 2 is not working. We would like to know the probability of working times not working times not working. That probability has to be largest. We have to choose a beta such that this outcome's probability is largest. Right, so how do we know the probability of it? We have to define a likelihood function. This likelihood function, f y given xi, equals to this monster here. It might seem intimidating, but remember, what we have derived earlier is that g beta tx is actually the probability of y equals to 1. So g beta tx is the probability of a person working. Remember that. G beta tx equals to the probability of people working. And so, what I've written down here is just that the probability of a person working times this thing here, 1 minus a probability of person of person working, means this is the probability of a person not working. And this whole thing refers to a single person only, refers to that observation only. If yi equals to 1, so the person chooses to work, then only this term stays behind, because look at this. 1 minus 1 equals to 0. A values to exponential to 0 equals to 1. So this cancels off. If a person chooses not to work, so yi, we plug in the value of 0, then this term equals to 1, so it doesn't matter. All that matters is this thing here. 1 minus 0 is 1, so this is the probability of a person not working. Remember, this f y given xi only refers to a single observation only. In my example earlier, we have 3 observations, so we will have to multiply the 3 observations likelihood. Why do we have to multiply them? Because in probability, if we want to investigate 3 outcome, it is the usual practice that we multiply them. A person work, the probability of a person working, times a probability of person working, times the probability of a person not working, for example. That whole multiplication, the whole outcome, is the probability that we have observed. So we want to make the whole thing times the whole thing largest, the whole probability largest. But that will be quite hard to maximize it because the whole outcome is a multiplication. It will be quite hard to find the maximum value of that. And that's why we need to make use of log. Log has 2 interesting features. First is that it won't change the value of beta that maximizes the likelihood function. And second is that a log can change multiplication to addition. And turning to addition can help us easier for maximization problem. So by taking log, we know that we can pull this yi here, and this is a natural logarithm, g beta tx, plus pull down 1 minus yi here, and natural logarithm of the probability of a person not working. And again, this whole thing is a log likelihood of a single person only. Remember earlier I said the whole likelihood function should be a multiplication of every person's likelihood. So times all that together, that whole chunk of likelihood function is multiplication. Taking log, we will split them off as of addition. And so the whole chunk of log likelihood should be a sum of the log likelihood of each person's. At the end, maximum likelihood means we choose a beta hat that maximizes this function. How do we do that? We just plug that into computer for optimization. We choose a beta to maximizes the sum of all the log likelihood. And the example that I've provided earlier is that after collecting samples from workers, their characteristics such as first person, age 20, gender female, choose to work, and a second maybe age 30, gender male, choose to not work, and so on. And after that, um, we times we put down the log likelihood function, and we just put it into the computer, and we can find the beta hat that maximizes this log likelihood function for maximization purpose. And that is the logic behind maximum likelihood.